All right. So I told you that here in this book, we assume that our cone is variable. I mean, for a unique y, we have a different cone. For any y, we have a cone. Unlike the first book of Gabrielle Eichfedler, where she assumed that k is constant in the problem of Pascoletti-Serafini, and so here we assume that d of y is variable, is not constant. Of course, here in this lecture, I will show you that if d of y is a set-valued map, if it is a local Lipschitz, then you can find a neighborhood. There exists a neighborhood such that d of y is constant. So let's move and so variable ordering structures are represented by cone-valued maps, by set-valued maps where the images are cone. For studying vector optimization problems with a variable ordering structure, it is important to have information about these cone-valued maps. And that's why, for example, we consider some concepts such as C-convex. So it is a generalization of all the properties or concepts of functions of single-valued, real-valued, traditional functions to concepts of set-valued maps, such as f, which defines for any y inside S a cone. So let's see what it means. So if a set-valued map is C-convex, as is written here, if it is C-convex, then f of x plus c is convex as well. Also, we can say that if f is a convalued map, if f is C-convex, then this relation holds. And a very simple proof. And another theorem which says that is if f is a cone-valued map, but f of x should be convex, then the intersection of all of them is a superset of C. You will see that in my last lecture, lecture 7, why this is an important theorem. And another lemma could be, for example, another properties of f. If f is a cone-valued map and f of x is a subset of C, where f is then f is a C-convex. You always use simple properties, so they are very straightforward. So an example of cone-valued map, which we need in all our algorithm, could be something like this. And it is obvious that f is a C-convex. And also, she introduced the concept of C-base convex. Remember that L is a functional space of functionals, is an element on the space of functionals. So if it acts on a vector, it becomes a scalar. And here we are going to define the concept of C-base convex. You remember that in BP cones, we define the cones like this. And here we have a lemma that says this BP cones, C of phi, it is convex. And it has some good properties because it is convex and we can use many useful properties. Another example of L, which we needed to define a cone, is like this. And Here we have a lemma which says that f of xi, if this relationship holds, then it is a constant set-valued map. So it's a constant set-valued map. And another example, you can define your functional like this, very simple. And the point I want to make is that we have some definition of lower semi-continuity. It is generalization for set-valued map. I mean, for example, in single-valued map, we have this. We have this function which is lower semi-continuous, but this is single value. For set-valued map, we have similar ideas. And locally Lipschitz, in this lecture, I wanted to say that this is the most important thing that I want to talk. Because if it is locally Lipschitz, if it's satisfied, if f is locally Lipschitz, for ordinary functions, you say that, for example, f of x1 minus f of x2 is less than alpha x1 minus x2. And this is the Lipschitz coefficients or Lipschitz rank. And here you generalize it for set-valued map. This is for single-valued, which is traditional Lipschitz functions. But here we are extended it. We are generalizing it for set-valued maps. And the important things is if f is locally Lipschitz, then you can see with a simple proof that locally there is a neighborhood. There is a neighborhood that locally f of x is constant. And it's a very useful property to connect different cones to make a unified cones. In the last lecture, I will show you why intersection of all these set-valued maps, intersection of all these cones, which is a constant, is important to define, to find some minimal elements, and we need it very much. So this is an example of locally Lipschitz set-valued map. And of course, we can generalize it using it. If we just make the intersection between fx and v, then this new concept, which is called locally pseudo-Lipschitz, you have defined a set-valued map that is not constant locally, and it has some useful properties. And of course, Jean-Pierre Aubin, and Jean-Pierre Aubin has written some books such as Set-Valued Map and Liability Theory, and many other good books. He is a French mathematician, and all of the set-valued map theory, and many of them are originally from him.